Hello again, this is the third video in my series covering the second part of the review of new technologies. In part 2A, we reviewed efficient electric technologies. Here in part 2B, we will consider flexibility technologies, including hydrogen and biofuels. Let us start with biofuels, which can directly reduce our dependency on fossil fuels. Biofuels can utilize a variety of feedstocks from energy crops through agricultural waste to wood chips. Processing typically involves thermal-based processes or anaerobic digestion to produce gas or liquids. This finish scheme takes an integrated view on waste treatment, supporting a range of local industries. Here in the UK, Drax is already trialling power generation using imported wood chips from overseas. Once produced, biogas could be blended to reduce the carbon footprint of natural gas. Bioliquids may also be the answer to longer-term decarbonisation of our industrial, shipping and aviation sectors. Ecologically sound biomass can be used for power, but there are still significant question marks over its sustainability and its impact on biodiversity. Moving to hydrogen, firstly, let's look at green hydrogen. Green hydrogen is produced from renewable power utilizing an electrolyzer. Electrolyzer technology is being honed as we speak, and different technologies and equipment scale are being tested. ERM are looking at offshore hydrogen production, which could possibly utilize existing natural gas pipelines to bring the hydrogen ashore. Currently, these technologies are expensive, and we don't anticipate significant surplus renewable energy at scale for a number of years. There is a small niche green hydrogen project being planned for Kent in the UK, where surplus energy at night from renewable wind farms can be utilised to produce green hydrogen to supply London's hydrogen buses. There is a longer term potential for green hydrogen as costs drop, but only once we have significant quantities of surplus renewable energy and it becomes routinely available. Then let's look at blue hydrogen, which most will know involves the reforming of natural gas to produce hydrogen with byproduct carbon dioxide sequestered into underground reservoirs. There are a number of depleted gas reservoirs in northwest Europe which could be used for carbon capture. This is still a developing technology, and as Shell, for example, is looking at improvements to the efficiency of their steam reforming processes, while many companies are looking at enhancing and reducing costs for carbon capture and storage. Blue hydrogen has significant potential to reduce carbon emissions over the next 25 years. They're ultimately segueing into a green hydrogen world. However, there's still question marks over carbon capture's scale up, though this technology has been practiced for many years. The success of the technology will depend upon reducing fugitive emissions from the gas production processes and to its economics. The latter will depend upon duties on carbon emitting fuels and or other government incentives. Having produced green or blue hydrogen, there is a need to transport it to the consumer. Much work is being done to look at repurposing our gas grid to hydrogen service. Technical and other safety case studies are well in hand, and later this year, the first results of the safety case work will become available. There are other challenges, including the changeover of transmission compressors to hydrogen duty. Though light, energy for energy, hydrogen requires over 3 times the compression horsepower to move it through our gas grid. It is unlikely that we will need to transition 100% of our natural gas energy to hydrogen, but even a 50% load factor should be possible through the current local supply grid, though this will require significant planning, as happened during the period when we transitioned our old coal gas system to the natural gas in the 1960s, 1970s. The availability of local resources, imports and multi-sector synergies are relevant to developing an energy transition plan. I have already mentioned offshore wind farms where Northwest Europe is well placed to become industry leader. North Africa can see a real opportunity to export green hydrogen, though, produced from solar energy in the desert, and Snam in Italy are already looking at repurposing their Transmed pipelines for hydrogen service, bringing hydrogen from North Africa into Europe. Further potential may exist to develop underground gas storage for hydrogen. Repurposing our existing natural gas trunk lines is also potentially feasible to ensure hydrogen becomes an internationally traded energy commodity across Europe. Experts are also looking at how we could ship hydrogen further around the world. Liquid hydrogen can be stored and shipped to minus 253 degrees C, almost 100 degrees colder than liquefied natural gas, which is shipped at minus 166 degrees C. However, other solutions are being sought, such as converting hydrogen to ammonia, which is already being shipped at scale for the production of fertilizers. Australia, with its abundance of wind, solar, and natural gas, are seriously looking at schemes to export hydrogen to Japan and China. More R&D is required to develop a fully liquid market for our future energy. It is currently expensive and inefficient, but over time, economics could still be driven by price arbitrage, as we have today with the international trade in LNG. Turning to uses of hydrogen, there will be few cases where hydrogen will be used directly to produce electric power. The first primary use of hydrogen is by industry. Indeed, industry already utilizes significant quantities of hydrogen produced from oil, which is called grey hydrogen, or coal, black hydrogen. The first steps of decarbonisation should be to clean up these processes with carbon capture. Industry is then looking at other means to reduce its oil and gas consumption, potentially using blue hydrogen as an energy feedstock, and the UK has 5 schemes currently under study. These are progressing to specific trials, such as replacing natural gas in glass making, with trials at NSF's Pilkington Glass Works. Where feasible, electrification is also being considered in industry. These projects and developments are being worked with the support from government, initially as they figure significantly in our national decarbonisation targets. Once off the ground, though, there will be an opportunity for synergies with other decarbonisation initiatives in the industrial regions, including transport and domestic applications. The next major opportunity use is in our homes. Already trials have progressed to introduce up to 20% hydrogen into our gas mains. This is the maximum feasible without change out of much equipment. Given the energy density of hydrogen, this only equates to a 7% saving on natural gas. Every little helps. 100% hydrogen boilers have already been developed and are under test. These can be produced as hydrogen-ready natural gas boilers at a small premium. And so with a service life of approximately 15 years, many boilers could be pre-installed before a changeover. Existing in-house pipework could be utilised, and cookers could be similarly converted. Their application is dependent upon a low-cost hydrogen supply, and again, more work is needed on standardisation. However, the cost premium is small, and existing gas installers can be easily trained to deliver this technology. The third mainstream use of hydrogen is within fuel cells. The earlier slide on electric vehicles included a UKCCC chart demonstrating the reduced efficiency of hydrogen fuel cells for vehicles. Another downside is that they require high purity hydrogen, which precludes the use of blue hydrogen without expensive purification. However, the higher energy density of hydrogen over batteries can make this the preferred technology for larger vehicles, ships, trains, and planes, and studies and trials are underway. Toyota have their Mirai car available for sale in Europe, and these are also being demonstrated at the Tokyo 2020 Olympics, which were being touted as the hydrogen gains. Fuel cells produce electricity, and so hydrogen cars could provide peak time power if connected to the local grid. Again, there is much work needed to prove up the technology and, where possible, provide standardization. Personally, I see the opportunity for hydrogen hybrid vehicles. These would bring the benefits of higher efficiency batteries for shorter journeys and hydrogen backup to enhance driving range. Let me conclude on new technologies by briefly outlining two areas where consumer demand can change our energy needs. Firstly, here I consider district heating for homes and other premises. This is not a new technology, as it has been long used in the old communist bloc countries. And even in London, we have a 70-year-old scheme close to my London flat in Pimlico. Typically, these utilise waste heat from industrial or power plants. In the case of the Pimlico scheme, with power from waste heat from Battersea Power Station. New fuels, renewables and heat pumps all offer opportunity for district heating schemes. However, this requires local level coordination and agreement, and is being considered by Mike Haynes with his local community in Dorset using heat pumps. The second common use area I would espouse is in public transport. Unfortunately, COVID has put many of us using public transport, but if we are again to reduce energy consumption, we need to reconsider our transport network. Again, this is not new, but insufficient attention is being paid by politicians to optimize our network. The steps needed to decarbonize the transport sector provide a window to rethink many established norms. The first of three examples here are electric bikes and scooters. They are already pretty well established, and in many places like London, they are becoming available for hire. The business model for these is still being refined, but young people in particular are taking on these technologies as a means to reduce their carbon footprint. The second example is the development of a hybrid train by a European consortium, one which can run on power on electrified lines, reverting to hydrogen when off-grid. The third is a new dimension to air travel, with a lightweight electric plane as being considered by Widerøe in Norway for short distance flights. We should try to capture the best of our new technologies to reduce our need for expensive and high carbon footprint equipment and products and maximize versatility. I hope this short review of new technologies has opened your eyes to the opportunities available to us. As we look forward, let us start by seeing how emerging technologies can contribute to our energy transition. These span supply, distribution, storage and use, and they center on two major themes: electrification and flexible fuels. Underpinning the success of these technologies are scale up and sustainability, consumer acceptance through standardization and low cost, a reliable delivery framework with competent and skilled workforce, and ultimately effective government policy. This concludes our review of new and emerging technologies, and I now encourage you to continue with the next video, which considers how some of the technologies can be utilized together in our future transition. Together, they will make up the what. Thank you.